This board, these next 4 sessions will be the last in the theory part of this chapter, and hence this whole course, because it's the last chapter of the book, chapter 11, on transitions, probability of transitioning from one initial state, UK, to some final state, UN, and increasingly statements made in the text by Davies and Betts, more of the nature, this is what's coming, rather than a full derivation. So expect that, right? And especially now at the end, because the two of them are finishing off their. This is an introductory text to quantum mechanics for people who have not done quantum mechanics before. So it's don't be surprised as increasingly over the next few sessions things are just effectively just thrown at you, and that's inevitable. You can't, at undergrad level, you can't derive everything fully at this stage. You just need more knowledge. So, but it's to give you a taste of what's coming, right? So now I'll just plunge in, continue on from the previous session. So the electromagnetic wave that gets applied, assume that it's not a pure frequency. Its frequency extends over a range. Let's say delta omega is the angular frequency, 2 pi f. Okay. Now assume that range is a lot larger than the peak, the sine squared term. The sine squared term in the integrand. Integrand just means the thing inside the integral that gets integrated, right? The integrand. Okay. And so, because the peak's fairly sharp, this range here, before we had an integral, go back to the previous session, we had an integral here over the range delta omega. But because the peak's pretty sharp, outside the peak, it's effectively 0, right? So that means outside the peak, the contribution to the integral is pretty well 0. So that allows you to extend the range instead of delta omega to plus or minus infinity, which simplifies the mathematics a lot. Okay? So that's why it's done. So it's another approximation, and you'll generate some error, but it's negligible. Okay? So you don't need to worry about it. Now, when your integral is now approximated, instead of being over this range, but plus or minus infinity, evaluating that integral gets a lot easier relatively, and it works out to be pi t over 2. Okay, you could try doing that. I haven't tried it myself. I'm not sure whether it's quite a trivial, or it may involve contour integration in complex analysis, which is my suspicion. But anyway, either way, when you evaluate this integral, you get pi t over 2, which is quite a simple form. Okay. Now put all these approximations together, and you'll end up with the transition rate. Right? Remember the probability of the transition occurring per unit time. So we're talking about a rate, the speed of this occurring, right? And it works out to be this. Okay. And this transition rate is equally valid. This formula here, equally valid for when the transition is upwards, in the sense that there's an increase in the energy of the system that's being modified, as downward, as there is a decrease in the energy of the system being modified. So upwards would be, for example, your starting state, your UK, has a lower energy than the state that gets transitioned to UN. Okay, And if it goes down, then your energy of your state UM would be lower than the energy level of state UK. Right? So it's this transition rate formula is equally valid for either up or down transitions. Energy going up or down. Right? So if the energy goes up, that means that some of that radiation has been absorbed by the system, and that radiation has energy, of course. So by conservation of energy, more or less, the energy of the system goes up, and so that's stimulated. Stimulated by the perturbing source. This electromagnetic waves is your perturbing source. Okay. So some of that energy gets, a quantum of it gets absorbed by the system, and its energy goes up. So that could be described as stimulated absorption of radiation. Right? Some of the energy of that radiation gets absorbed. In other words, a photon gets absorbed. Okay? And stimulated emissions the other way, where the energy goes down, and so in Bohr's model that would mean a photon is emitted, right? So stimulated emission of radiation. Okay? So the energy then would be less than what you started with. Here the energy is greater than what you started with. Okay? Now there's a sort of classical analog. It's just thrown it. I mean, a lot of you be warned. This is the last 4 sessions of the textbook, right? The course is almost over. Now I still have a backlog of problem-solving sessions that I need to film. Quite a few actually. I've left that till you. But in terms of the theory portion of the text, these 4 sessions, that's it. That's the end of the course. And then I will change hats entirely and start doing a computer theory course. So those of you who are interested also in following me on a computer theory course, here's the text that I'll be using. It's a rather famous text, almost the Bible in terms of theory of computation. It's by Sipser, S-I-P-S-E-R, so just one author this time. Now I have a Chinese version. Well, I mean the text is in English, but well, you can just see. And I can't read the Chinese.